In the beginning, there was no shape, no color, no sound, only an endless ocean of energy, hot, furious, and indivisible. But that ocean did not stay still. It churned, it cooled, it fractured into the first patterns of existence. And from that ancient storm, a strange thing emerged, the building blocks from which everything you have ever known would be made. Atoms. They are the silent bricks of reality, invisible yet everywhere. Every mountain, every drop of water, every living breath you've ever taken is woven from them. The gold in a wedding ring, the calcium in your bones, the oxygen in your lungs, all of it bound together by a language written in the heart of matter. But why this? Why should the universe choose this peculiar size, this delicate balance of energy and emptiness, as the foundation of all things? Why not something smaller, stranger, or infinitely divisible? The question haunted us long before science had a name for it. 2,500 years ago, in the sunlit courtyards of ancient Greece, a man named Democritus dared to imagine the impossible. He saw the world not as a continuous whole, but as a mosaic, tiny, indivisible pieces separated by the void. He called them atomos, the uncuttable. To him, atoms were eternal without birth or death, drifting through empty space to form all that exists. It was a vision so alien, so ahead of its time, that it would take humanity more than 20 centuries to catch up. In the ages that followed, this vision dimmed, empires rose and fell. Knowledge was lost and rediscovered, and the idea of atoms became less a truth than a whisper, a rumor carried forward by scholars who saw in nature an unseen order. But the cosmos had other ideas, and in time it would reveal to us that Democritus had only glimpsed a fraction of the truth. Atoms were not indivisible. They were not eternal. And their story was far older, far stranger than anyone could have imagined. For to understand why everything is made of atoms, we must journey to a time before atoms existed, before stars, before galaxies, to the first moments after time itself began. And there, in the blinding light of creation, we will find our answer. Before there were atoms, there was chaos. Not the chaos of storms or earthquakes, but a far deeper kind, a cosmos so hot, so dense, that the familiar rules of matter simply did not apply. In that first fraction of a second after the Big Bang, there were no protons, no electrons, no atomic structure at all. Only a seething ocean of pure energy where particles flickered into existence and vanished again before they could take shape. Quarks, the smallest known building blocks of matter, swam freely in this blinding plasma, bound together by gluons, in an unbroken dance of creation and destruction. Time itself was young enough to be measured in heartbeats of the universe's own pulse, trillionths of a second, then millionths. As the cosmos expanded, it began to cool, and for the first time, quarks locked together into trios, forming the first protons and neutrons. These were the bare seeds of what would one day become the nuclei of atoms. But even now, there was still no such thing as an atom. The newborn universe was still far too hot for anything delicate to survive. It would take minutes, an eternity, by the standards of those first moments, before conditions settled enough for the next step. When the cosmic furnace cooled to roughly 1 billion degrees, a remarkable process began: nuclear fusion on a universal scale. Protons and neutrons smashed together to form the simplest atomic nuclei, mostly hydrogen, with a scattering of helium and traces of lithium. This was primordial nucleosynthesis, the forging of the first elements from the raw fire of creation. And yet in this act of birth, there was also limitation. The universe expanded too quickly for anything heavier to form. Carbon, oxygen, iron, these would have to wait for the birth and death of stars. For now, the cosmos was a thin, hot fog of the lightest elements, still without electrons bound to them, still without the familiar architecture of atoms. It would take hundreds of thousands of years more before the universe cooled enough for electrons to be captured, wrapping themselves around those tiny nuclei and bringing the first true atoms into existence. Atoms had been born, but they were not yet arranged into the worlds, the oceans, and the living creatures we know today. For that, the universe would need new forges, and those forges would burn in the hearts of stars. The first atoms drifted through a universe without structure. They floated in darkness, scattered across expanding space like dust in an endless night. There were no galaxies, no suns, no worlds, only a quiet sea of hydrogen and helium stretching from horizon to horizon. But gravity had been patient since the first moment. It reached across the void, pulling atoms together into invisible clouds. Over millions of years, those clouds thickened, grew heavier, and began to collapse. Where the pressure rose high enough, matter heated, until the darkness cracked with the birth of the first light. Stars. In their cores, the temperatures soared to millions of degrees. Here, the simplest atoms were pressed so tightly together that their very nuclei fused, becoming something new. Hydrogen transformed into helium, releasing a flood of energy, the heartbeat of a star. It was the same process that had forged the earliest helium in the Big Bang, but now it was happening on a grander stage in cosmic furnaces scattered through space. As stars aged, the fire in their cores grew hotter and more desperate. They began fusing helium into carbon and oxygen, the skeleton of all future life. In the largest stars, fusion pushed further, still, neon magnesium, silicon, until finally iron. And then the forges faltered. Iron does not yield energy when fused, it consumes it. In that moment, the star's balance collapsed. Its core imploded under its own gravity, and the outer layers rebounded in a cataclysm so powerful it outshone entire galaxies. A supernova. In the heart of that explosion, for a few fleeting seconds, nature could forge the heaviest atoms, gold uranium, and dozens more, scattering them at incredible speeds into the surrounding void. Some of these elements came from an even rarer source, the collision of neutron stars where matter crushed beyond imagination hurled out precious metals in titanic jets of debris. Over billions of years, these cosmic ashes mingled with clouds of gas, seeding them with the ingredients for planets, oceans, and life. Every atom in your body heavier than hydrogen, every carbon atom in your cells, every oxygen atom in your blood, every calcium atom in your bones was born in a star's heart and released in its death. We are quite literally made of stardust, but atoms alone do not explain why the universe is built the way it is. To understand that, we must journey inward, past molecules, past nuclei, to the strange quantum realm that decides the very size of an atom. At first glance, the atom seems impossibly small, far beyond the reach of our senses. Billions could line up across the width of a single grain of sand. And yet, compared to the subatomic particles within it, the atom is vast, a cathedral of empty space, with a dense nucleus at its heart, and electrons moving in ghostly orbits far from its core. Why this size? Why this architecture? The answer lies in a balance of forces so precise that if altered by even the smallest fraction, the universe as we know it could not exist. At the center of every atom, the nucleus is bound together by the strong nuclear force, nature's most powerful glue, holding protons and neutrons against the intense electromagnetic repulsion of their positive charges. Outside the nucleus, electrons are held in place by electromagnetism attracted to the protons, but unable to fall directly into them because of the strange rules of quantum mechanics. In the quantum realm, particles are not points, but waves and electrons can only occupy certain standing wave patterns around a nucleus. Shrink the atom too much, and the uncertainty principle pushes the electron's energy so high it escapes entirely. Enlarge it too much, and the pull of the nucleus becomes too weak to hold the electron at all. It is this dance between the electromagnetic pull inward and the quantum pressure outward that fixes the atom's size at roughly 1/10 millionth of a millimeter. This is the scale where chemistry happens, where bonds form, where life is possible. Change the rules even slightly, and reality itself would warp beyond recognition. If the strong nuclear force were weaker, the nuclei of atoms would fall apart. Hydrogen would be the only element in existence. If it were stronger, all hydrogen would fuse instantly into heavier elements, leaving no fuel for stars to shine for billions of years. If electromagnetism shifted in strength, the very geometry of the atom would stretch or collapse, erasing the stable chemistry on which life depends. Atoms are not just the building blocks of matter. They are the meeting point of the cosmic and the quantum too small, and the rules of the universe dissolve into a chaos of particles. Too large and matter loses the complexity to build worlds. The atom's size is not an accident. It is a compromise struck in the first moments of the cosmos that allows the vastness of the universe to be built from the smallest of foundations. And from these foundations, layer upon layer, the architecture of reality emerges: molecules, minerals, planets, and life. To see how we must step back and watch the atoms assemble into something greater. From the quiet order of the atom, a new kind of complexity begins. Atoms reach out to one another, sharing electrons, locking together in bonds that form the first molecules. Hydrogen pairs with oxygen to make water. The universal solvent, carbon chains link into endless variations forming the backbone of biology. Nitrogen, phosphorus, sulfur. Each adds its own chapter to the growing chemical library. These molecules gather not in isolation, but in clouds, vast nebulae enriched by the ashes of long-dead stars. Gravity draws them inward, spinning them into disks of dust and gas. In the center, new stars flare to life around them, planets begin to take shape. Some worlds become scorched deserts, others frozen wastelands, and a few balanced in the narrow band between heat and cold hold the conditions where liquid water can flow. On such worlds, atoms find new ways to arrange themselves. They build crystals, minerals, and rocks. They shape atmospheres and oceans. In the right circumstances, they even begin to copy themselves, giving rise to the first primitive life. From here, the patterns grow more intricate. Cells form powered by chains of molecules working in precise harmony. Over billions of years, these cells combine into creatures of staggering complexity. Corals and whales, forests, and fungi minds capable of asking where they came from. Yet, for all this diversity, the foundation never changes. The calcium in a seashell, the iron in your blood, the silicon in a computer chip, all are atoms, born in stars, and bound by the same quantum rules. Across the universe, from the rings of Saturn to the mountains of Mars, the same atomic structures repeat. This is the universality of matter, the same architecture built from the same bricks everywhere. A hydrogen atom on the far side of the galaxy is identical to one here on Earth. The laws that shape them are indifferent to distance, time, or place. And so the cosmos is not a random scatter of things, but a great cathedral of matter rising from the atomic scale to the galactic atoms are its stones, chemistry, its mortar, and gravity, its master architect. But even stone can crumble. And the atoms that make up our world are not eternal. To understand their true story, we must follow them into the far future to see how they change, decay, and perhaps, one day, disappear. Atoms seem eternal. The iron in an ancient sword, the gold in a pharaoh's mask, the oxygen in your next breath all endure through centuries and millennia, cycling from form to form without losing their identity. They are passed from one thing to another, from rock to river, from leaf to lung. In this way, atoms carry a kind of immortality, and yet they are not unbreakable. Some are unstable by nature, their nuclei too heavy or too unbalanced to last forever. These radioactive atoms decay, spitting out particles and energy transforming into new elements in the process. Uranium becomes lead over billions of years. Carbon-14 fades into nitrogen, leaving behind a clock that lets us read the ages of fossils and ruins. Even the most stable atoms face a longer fate. In the deepest future, trillions upon trillions of years from now, theories suggest that even protons, the very heart of atomic structure, may decay. If this is true, then no atom will survive the endless march of time. One by one they will fall apart into simpler particles until nothing remains but a thin haze of energy. Before that distant end comes other transformations. In the death of stars, atoms are torn apart and reforged in new combinations. On the surfaces of neutron stars, pressures crush them into strange forms of matter never seen elsewhere. Near black holes, atoms are stripped of their electrons and broken down into their most basic pieces. But for now, for the brief window in which life and worlds exist, atoms are stable enough to build mountains, oceans, and living beings. The hydrogen in your blood is older than the Earth. The calcium in your bones was forged in an ancient supernova. The gold on your finger may have been born in the collision of neutron stars before the sun was even lit. When we look around, we are not just seeing the present. We are seeing a chain of transformations stretching back to the dawn of time and forward to a future where atoms themselves may vanish. They are fragile on the scale of eternity, but to us, they are the most enduring things we will ever touch. And so we return to where we began, to the idea that everything is made of atoms. It is not merely a statement of physics, but a truth that binds us to the cosmos. From the first fire of creation to the quiet end of time, atoms are the common thread. They are the storytellers of the universe, and through them, so are we. From the searing brightness of the Big Bang to the quiet darkness of the present, atoms have endured. They are the handwriting of the universe, etched in a language older than stars, older than worlds, older than life itself. They began as fragments of pure energy, born in the first trembling seconds of time. They gathered in clouds, lit the first stars, and from the fires of those stars came every element. We know the gold in our hands, the oxygen in our lungs, the carbon that shapes every living thing. They built mountains and rivers, they formed planets and moons, they assembled the chains of molecules that learned to copy themselves, and in time, to think, to wonder, to ask. Atoms do not care about us. They have no purpose, no plan. And yet, through their patterns, galaxies, spiral oceans shimmer, forests grow, and minds awaken to gaze back at the night sky and ask why. Every breath you take passes atoms older than Earth through your body. Every meal you eat is a temporary borrowing from the universe's endless cycle of matter. And when you are gone, those atoms will return to the sea of existence, ready to be shaped into something new. A blade of grass, a distant moon, perhaps another being who will one day ask the same questions. In the end, we are not separate from the universe. We are the universe arranged for a moment into a form that can see itself. Atoms are the bricks. We are the cathedral they build, lit for a fleeting instant before returning to the dark. Everything is made of atoms, and in that simple truth lies the most profound connection of all that across all of space and time. We are bound to the stars, to each other, and to everything that ever was or ever will be.